I wanted to say that there's a paper, an expository paper on the non-equivariant homology of the little disk Soparad that I wrote, that if you enjoy that example, if you want to see a little bit more of these ideas in action, there I mentioned tome cochains, but I use pullbacks, and remember how we said that you can usually in studying the homology and cohomology of a space, you find interesting maps in and maps out, and calculate induced maps, and eventually piece it together by, and that can include, for example, filtering a space and taking subquotients and calculating their homology. Those are various maps in and maps out if you trace through that, broadly speaking. So in any case, I didn't exclusively use tome cochains there, but you can look at that survey if you'd like. I also talk about those spaces quite a bit in the lecture series I also have on my YouTube page on algebraic topology from a geometric viewpoint, which is very much the philosophy that we have here. So let's continue. We were talking about various ways that tome cochains, we can put them to use. One is to just produce cohomology. Two is to explicitly fully present it, homology, cohomology, and cut product. And three is to start talking about Poincare duality at the chain level. And then the other thing I wanted to lump in here, because they kind of go together in my mind, is to talk about models. So the point is that if M is closed and oriented, and then we have this W with a map to M, again, for convenience for cohomology, we factor it as through some map to a fattened up version of M. Then if M is closed and oriented and W is closed and oriented, then what we would get is, first of all, if we would have the image of the fundamental class of W, and that's in the Dth homology, so this is D-dimensional as well. And then you would have the tome class of W in the N minus Dth cohomology of M. And so we see that that we're using the same object to represent homology and cohomology, so that you could actually prove Poincare duality this way if you could put these tome cochains in appropriate chain complex. Unfortunately, I mean, let me already say that the natural thing for manifolds and boundaries, that's a chain complex that gives you cobordism, hence the name tome cochains or tome chains if you were thinking of them in the first way. You could make a chain complex with manifolds with boundary, and they kill their boundaries, but it's kind of a silly chain complex. Not too much is piecing together, and so so I think you basically get cobordism, because if two things glue along a boundary, then you could have smoothed them out to begin with. There's a little bit to check, but I'm pretty sure that the chain complexes you make here are realizing bordism or cobordism. But you could use manifolds with corners, and then you can try to realize the two objects. Let me say more about that in a bit. The point is then that that our calculations for a complete presentation really becomes, if homology and cohomology are represented by the same objects, you've really got a spanning set with inner product. Instead of a spanning set and a co-spanning set and a pairing, you really have an inner product. And in some ways, a manifold without boundary is a vector space within your product. There's a lot of mathematics that proceeds by just kind of seeing manifoldness as at a most basic level, this inner product idea. Of course, it's sort of graded, right? The inner product is only defined when I've got things of complementary dimension. We of course know that there's more to it than that. So let's remember that to find products. So this is the additive story. Is you just have an inner product. To find actual cut products, well, if you think about it for a moment, you would find that you would want to, if I'm taking, again, in good cases, I'm taking closed submanifolds, submanifolds without boundary or cochains. This is in the case where the ambient manifold is compact, so these are really closed submanifolds then without boundary. And I'm trying to find out what that product is by evaluating it on the fundamental class of U. I could say F lower star of the fundamental class of U or something like that, if F is its reference map. And well, that ends up being, if everybody's transverse, just the number of intersection points of the triple intersection of V, W, and U. And of course, triple intersection is symmetric. So that speaks to, and this is just true in general of duality. So Poincare duality with cut products means I've got a trilinear form encoding the product to the ground ring Z if I'm oriented in torsion free, or maybe I want it to be a field if I really want to talk about good trilinear forms, which are non-degenerate. So this is the object in question, and it's really about, in this point of view, it's about intersection. And this is not. This is a very time-honored perspective. And in fact, various kinds of algebraic geometers, especially those who are more, they might even call themselves more algebraic combinatorialists who do some algebraic geometry. I think of somebody, his name is Young at Illinois, studies these trilinear forms for beautiful manifolds, Grassmannians, and their generalizations in various settings. A nice little example here. We're so used to the cohomology rings of projective spaces are polynomial. But if, for example, we think about if I plus j plus k equals some n, then in general position, a CPI intersect a CPJ intersect a CPK in CPN is going to be, or let's see, sorry, I should say n minus I, n minus j, and n minus k. That's going to be 1, just a single point. And this data is equivalent, and this is, by the way, just a fact of linear algebra. This is, in essence, one of the main things that that we define projective spaces for, is to have this kind of intersections happen very generally. You add the points at infinity so that every 2 lines in the plane intersect in a point, etc. And in this case, this basic fact that comes almost from the definition of complex projective space that implies that the cohomology of CPN is polynomial. But but again, I like to have that GM, so that this polynomial ring is witnessing this lovely geometric fact. And and yeah, there's a lot of games that people play with these sort of trilinear pairings when once you apply duality to have some fun combinatorics and geometry married within the study of these cohomology rings. So let me talk about, let's go back to this idea of Poincare duality at the chain level and related matters. So let me talk about both some limitations and some open questions. So again, so we can make a chain complex from Thom objects, or maybe I should call them Quillen objects. These maps with by the Stokes theorem, this defines a cochain map. That's again sort of that Stokes theorem is giving you so this would be a cochain complex if we're working cohomologically. That's because the co-boundary of tau W is minus tau boundary W. But it's a little tricky. First of all, what you want is that so Thom, the chain complex, almost by definition represents Bordism. Quillen used these objects, the closed objects, represent, and let me even say, I'll make a, the closed objects in cohomology so closed in the sense of no boundary, but not closed in the sense of compact with no boundary. But we only need proper for cohomology. Those objects represent, in the case that we've been talking about, would be oriented cobordism. So that's part of the motivation for these definitions. It's extending one of Quillen. So what we can do is, if there are W's have corners, so that would include simplices, we can recover chains and cochains. So so that's chains and cochains that calculate homology and cohomology, not cobordism. So you can check that in particular, Stokes theorem looked, you pull back this codimension, this object, which is of sufficient codimension to give you a one-dimensional pullback, and will be a manifold with corners in the corner setting, but a one-dimensional manifold with corners is still a manifold with boundaries. So the theory works perfectly well if we both have simplices mapping in, something like singular chains, and simplices dually. So, but there is a technical issue. in comparison, namely we can't have too many chains or cochains simultaneously. And so this is just to make sure that folks know, again, for the applications that we're going to be making, just a single closed, single manifold with no boundary that maps in properly, that gives a cohomology class. And that's again, the very first thing I talked about in this lecture, application number one, so to speak. This is more subtle. So, the point is that that what you'd want to do is have these tome cochains compare with the smooth, all smooth cochains. But again, it's you would need some transversality. I won't talk about a reference manifold M. These are all in the same manifold. And so what you do is, but so again, there's nothing, there generally will be no comparison map like this. So what you often need is some other object in the middle here that helps us compare to both. For example, and what you have to do is make one side or the other much smaller. The point is a tome cochain can't evaluate on every smooth chain. So when we took a single tome cochain or a finite set, so let me, if S is a finite collection of manifolds, then inside the tome cochains, I could just look at the tome cochains of those manifolds. And then the point is that if I've got a finite number of submanifolds, then inside the chains, I can be transverse to all of them, which means inside the cochains, I would find the ones that are transverse to S as a quotient, and I can map inside here. I'll just say CS upper star is inside here, and I can and I do have a map. So on the left side, I'm finite. On the right side, I've cut things down. The point is that if on the left side I am in particular not locally finite, then in particular if I considered all tome cochains, then there would be nothing transverse to every one. And so this the thing I want to try to define, C transverse to S, if S is too big, it becomes 0 because there's nothing transverse to every other map that's sort of an object of complementary dimension. So that's one option, is to cut down the left side to make it finite. Or I can do the same with the right. Instead of all singular chains, this is much more familiar, I pick some sort of simplicial complex structure. An application I'm working on now would be cubical, but it's certainly the same spirit. And then within the tome cochains, I can look at the ones which are transverse to the cubical structure. And then there's a map this way, which is good for comparison. So you just need to, you can't take all singular tome cochains and all smooth cochains and compare them readily. You only get comparison maps if you either only consider a finite number of tome cochains, in which case you can cut down your chains on which you evaluate, but still have a quasi-isomorphic theory, or if you're willing to do something like have a simplicial complex structure, then you also get a comparison here. And I'm in the process of writing up some work now with Greg Friedman and Anibal Medina, where we realize that this has, on this side, we've got a partially defined commutative product by pullback or intersection. Over here, of course, we have a, the standard associative product. It's not commutative, right? Cut product is not commutative. It is the infinity if you want, right? And we've got this comparison, and this doesn't commute, but this map will of products is we don't preserve products, but the neat thing is, but have a chain homotopy defined through flows, through vector field flows, some particular vector fields that we that arise from, again, I make it a cubical structure here, flows, which relates these commutative but partially defined on one side to only associative but E infinity on the other. So this is kind of trying to have both geometry and commutativity, but partial definedness, and all the rigid simplicial algebra or cubical, actually, in the same picture. So that's just a picture of, yes, what happens when you try to make these tome cochains evolve, not just from I can produce a single cohomology class, or not just from a cohomology basis, but can I have a theory that really captures chains, cochains with some multiplicative structure? And it's something that is something I'm researching now. So I wanted to share a bit of that. Okay, I think we'll end the broadcast. And